Alright, hello and welcome back to Robopolis. Today is Monday, September 20th, and since it's a Monday, we will be doing AP Physics 1 content. So I'm really excited about today's lesson. It builds a lot on the previous lesson. So if you're joining this on Twitch, welcome. And if you're watching this on YouTube and you haven't checked out the previous video on one-dimensional kinematics, it might be a good idea to watch that and get a bit of a refresher on that information, because today's information will build off of it. And don't worry, I will be talking a lot about that content in today's lesson, but maybe it'll help you out if you view that video first. So, with that said, I don't think there are any other announcements. Let's just jump right into the content. I'm pretty excited. Okay. So, as you can see, today we're talking about kinematics in 2 dimensions. So, last week we talked about one-dimensional kinematics, as I just talked about, and that was about objects moving in a line, right? Back and forth in a line. That's just one dimension. Now we expand to 2 dimensions. So now we can do a lot of really cool stuff, and this is where physics really gets to start, really starts to get fun. Because now we consider things moving in the air, flying through the air, because we have the x direction and y direction now, or perhaps x and z direction, it doesn't really matter, but now we're seeing how objects move in 2 dimensions. So, let's just jump into it, and as always, the textbook reference is on this slideshow, and you can feel free to check out that textbook, which is free, and, read the chapters and get some more practice problems. So as we can see, we're going to start talking about vectors today. So we talked about vectors a little bit last time. We talked about what they were, that they are quantities that have both size and direction. And because of that, we can represent vectors as, well, arrows. And why is that? Well, we can represent size by changing the size of an arrow, making it larger or smaller. And arrows provide a sense of direction because they have a pointer, which we call the head. So in this little diagram at the bottom, that's called the head, and the bottom part here, that's called the tail. And in fact, what we can do is we can add vectors. And the reason why I use the vocabulary of head and tail just now is because the method of adding vectors is usually called the head-to-tail method. That is one way of adding vectors, and I'll briefly describe that now. So we can see that if we have 2 vectors, essentially what we do is we take the tail of one vector and add it to the head of the other vector, and then draw what we call the resultant vector from the tail of the first vector to the head of the second vector. So, this is going to be fun. If this is the first vector, right, let's say my elbow is the tail, and my fingertips are the head. And then we have another vector, which it's going to look like this because my hand doesn't bend that way. But let's just say this is the tail of the vector, and my fingertips, again, are the head of the vector. Then if we were to add these 2 vectors, what we do is we take the first vector, and then we take the tail of the second vector, which is my wrist, and in the same orientation, we just place it on top. And then the sum of these 2 vectors would be the vector starting from my elbow to the fingertips on this hand that I'm wiggling right now. So if you can imagine that, what that would look like. Unfortunately, I don't have a third arm, but that's how the head-to-tail method works. And we can see it a little bit better without hands in this top diagram, right? So we have this first vector here, and we have another one here. And an important thing we want to do is we want to make sure we're not changing the direction of these vectors. So when we add them head to tail, the first vector, I keep where it is, right? And it's at the same angle. It's pointing in the same direction. And then the second vector, I put the tail of it at the head of the first vector, right? Right there. And still, it's pointing in the same direction, right? This is the same direction as this, or at least approximately, right? And now we can see that if we draw the resulting vector from the tail of the first vector to the head of the second vector, that's the vector sum. So that's one way of adding vectors together. And another way of adding vectors is to do it by components, because vectors at angles have x components and y components. And we see that down here. So we have this vector at an angle, and essentially what we can do is we can draw perpendiculars from the head of the vector. So we can draw a perpendicular downwards and to the side. And when we do that, if we draw a vector to the point that we reach on on an axis, right? So we'll imagine an x and y axis. If we draw this vector, we get what's called the x component of the vector, and similarly, this is the y component of the vector. And you can kind of see why, right? In a normal Cartesian plane, we have the x-axis going horizontally and the y-axis going vertically, right? And they're called components because if you add these components together, you'll get the vector v. And if you don't believe me, you can just do the head-to-tail method that was described, and you'll see that, oh wow, we actually do get v, which is pretty good. So, what can we do from here? Well, we can actually find the magnitude of these components, right? We can find the x component and the y component respectively. So here I have labeled some value of theta, which is an angle. And from that, we can use some trig to get the components. So if we take the cosine of the angle, so cosine is equal to the adjacent over the hypotenuse. And what we're doing is we're looking at this triangle right here. So the adjacent side to this theta is the x component. So we can say cosine of theta equals x, and the hypotenuse, well, that's just this vector v, right? And so we can solve for the x component. Maybe I'll label it v sub x. And we can see that when we do that, we get this quantity right here. Similarly, if we do sine of theta, we'll get sine of theta equals opposite over hypotenuse. And there's a couple of ways of looking at this. Suppose we look at the same triangle here. What would the opposite to theta be? Well, it would be this side right here. And this side is identical to this side, because everything is right angles. You know, we defined these components by dropping the perpendiculars from the head of v. So we can just say that that is vy. Another way of looking at it is if you remember geometry, interior angles are congruent when you have parallel lines. So essentially this angle up here is also theta. And then if we do sine with this triangle, you can see that the opposite side is this one, which is what we define to be the y component. So this evaluates to vy over the hypotenuse again, that's just v. And then if you solve for vy, you get v times sine theta. Now, important here, I said notice theta. What does that mean? Well, what I mean by that is just notice where theta is defined. If, for example, we defined this angle instead, and I'll use the Greek letter phi for that, then these equations over here would not hold, and you can test them out. Because, for example, cosine of phi is equal to, well, let's look at this triangle again. What's the adjacent side to phi? That's this, so that's vy, and now the hypotenuse is still v. So this tells us that vy equals v times cosine of phi, where here it was sine theta. So we have to be careful where these angles are defined with respect to which components. And then, since we're dealing with, you know, triangles and stuff, we can still use some of the rules of triangles that we know. For example, this right here, that's just the Pythagorean theorem. So if we had the x component and y component of the vector, we could find the actual vector by just using the Pythagorean theorem. Similarly, if we're given the two components, we can find the angle theta in this case just by using the inverse tangent. And similarly, phi would be the inverse tangent of Vx over Vy. So that's a quick review about vectors. Now we sort of know how to add vectors. And this helps when we're doing 2 dimensions, because now not all of the vectors are pointing along the same line. We're pointing in different directions now. It's a little more exciting. But first, let's talk about projectile motion. So really, when we talk about kinematics in 2 dimensions, almost everything we do in this unit involves projectile motion, which is just a fancy term for something flying through the air. And that makes sense, right? When you think of a projectile, you think of or at least I think of a little ball or like a bullet or something like that. And the motion of it, well, it flies through the air, right? So that's all it is. Now, an important thing to notice is that if it's flying through the air, the only acceleration the object is experiencing is the acceleration due to gravity, right? Because we've established that gravity is almost always there. We will be dealing with instances where gravity is not a force, but in almost all cases, the gravitational force is there. And so we will be experiencing the acceleration due to gravity. So remember, A equals plus or minus 9.8 meters per second squared. And notice that I put plus or minus right here. That's because this depends on how we define the direction. Typically, we define the higher you go up in the air, it's positive y, whereas the closer to the ground is closer to y equals 0. So in that case, acceleration would be negative because it's pointing in the downwards direction. And then finally, a little tip here is to separate the problem into the x components and y components. And this might seem a little confusing right now, but it will make sense when we do more problems. But we can sort of see what's happening right now. If we have something flying through the air, it has a velocity, which is a vector, and if the vector has both an x component and y component, it might be difficult to see how those components are changing with time as something flies through the air. So separating them into the x parts and the y parts can be really helpful. Alright, cool. Let's move onwards. So kinematic equations, and again, I say to memorize these. And it's actually a funny story. A couple of days ago, I was talking to a friend of mine, and they asked me about the kinematics equations, and I had to admit to them that I'm a little shaky on them. I don't remember them immediately, and after a couple of minutes, I finally thought about all of them. But it was kind of embarrassing. So we sort of just sat down together and we just memorized them. So now I feel pretty good about them. So if you memorize them now, you won't have to worry about turning back to these whenever you do kinematics questions. So I said this last week, and I'll say it again, memorize these, it'll save you so much time. But anyways, these 3 on the left, they should be quite familiar, because these are the 3 equations that we presented last week when we did one-dimensional kinematics. And really, they still hold. They still hold true. And there's 2 new ones on the right, but these aren't really that new. We've seen these in some form before. This first one, well, this can be, changed into xf minus x naught equals v times t, which just means that delta x equals v times t, which just means that v equals delta x over t. And that's just the definition of velocity, right? The change in position with time. The displacement divided by the time. It makes sense. This is just another way of writing it. And the second one here, that's just saying the average velocity. What you do to get that is you take the starting velocity and the ending velocity, add them up, and divide it by 2. You're just taking the average of 2 numbers. So the 2 on the right are pretty self-explanatory. So really, we already know all the equations we need for kinematics. Well, in 2 dimensions. And 1 dimension, because that's what we did last week. So, there's not much new to learn when it comes to formulas. So here we have this nice visualization of a soccer ball. So we can see that now, okay, the soccer ball flies through the air, and it's traveling in 2 dimensions, right? It's not just traveling along this line from one point to another. It's flying through this air along this dotted line path. And so we have an x direction and a y direction. And for simplicity, I'll just say that this is the positive x direction as we go this way. This is the negative x direction as we go this way. This is the positive y direction, and this is the negative y direction. So, from the starting point, where y equals 0, right, we'll just say that this is y equals 0. The ball flies up until it reaches some point at the top, and that point will be quite critical momentarily, and then eventually it falls back down. And I'm sure most of us have kicked a soccer ball or seen some sort of ball flying through the air. We know that when you kick it up, it comes down. And why is that? Well, our good friend gravity helps us out. So that's right here. We have this downwards acceleration. And since we defined the directions of x and y in this case, acceleration should actually be negative 9.8 meters per second squared, because it's pointing in the negative y direction. Is there any other acceleration? No. I don't know what else could possibly be providing an acceleration. We have this ball, it's just flying through the air. So along this dotted line, I've created the vectors, well, at least the components of the vectors at each position. Because the real vectors, they just follow the dotted line path. For example, at this point here, the real vector is something like this, right? It's following the dotted line, or rather, the ball follows that vector because it describes the direction of motion. And we can see that if we draw the dotted lines down, the perpendiculars, we get these components. So what do we notice? As the ball flies through the air, it doesn't matter where we are, but this x component is the same at every point. It's the same magnitude and it's the same direction. And this is an important quality of two-dimensional kinematics. When something is flying through the air like this, the velocity vector in the x direction stays the same. So, let's ignore the y direction. If we were just considering one-dimensional kinematics, and we saw that the velocity vector is the same throughout, what would that tell us? And if you look at last week's lesson, we saw a couple of examples of this where we saw pictures of arrows and we made some conclusions. We concluded that the ball would be experiencing no acceleration, which is good because we said there was no acceleration in the x direction. The only acceleration there was in the y direction. So that is an important quality and something to always remember. So what happens to the y direction? Well, as we can see, it starts out with a really good, really strong y velocity, which makes sense, right? Because the ball is ascending into the air. But gravity is pushing it downwards, which means that that velocity will eventually reach 0, which is what happens at this critical point right there, the peak of the curve. At that point, the ball has reached its maximum height, and now gravity is going to take over and make it go back down to the ground. So at this critical point, the y velocity is 0. And this should make sense because it temporarily stops there. You know, it starts out going up pretty quickly, and then it slows down until it momentarily stops, and then it comes back down. So there's I'm just going to write it here. Y velocity equals 0. That's another very important thing to remember. But we can see that, you know, it starts out pretty big and then it gets smaller until it gets to 0, and then the y velocity is in the opposite direction because now it's traveling back downwards. Another important thing to know is that this curve that it follows is symmetric. it is symmetric from one side to the other. And what we can see is really, if we look at this set of vectors and this set of vectors, we saw that the x component stays the same. Another very important thing, there's a lot of super important things to know about this, is that the y component, it's equal in magnitude, but opposite in direction. So, I'll write it down. From one side to the other, I guess to the exact other side, what happens? Well, x component, I'm going to abbreviate, stays the same, and then y component, well, there's two things to consider. Magnitude, meaning like the size of it, stays the same, is the same, but direction is opposite. And it's exactly opposite. Because when we're just considering the y direction, that's one-dimensional. It's just up and down. So either you point upwards or you point downwards. There's no angles that we have to worry about. So this is why I really stressed in the beginning that we have to break the problem into the x component and the y components. Okay, couple other things is that we define from the starting point to the ending point, that's delta x. That should be quite familiar, right? It's just the change in displacement. But also we have this new quantity delta y, which is pretty similar, right? Delta is change, y is just the measure in the y direction. So that's just displacement in the y direction. And at this peak, delta y is at its max. But we can still have, some delta y here or here. And I wonder if you can guess, at the same point, of reflection, so if we reflect the point from here to the opposite side along this, center line, the point of symmetry, like these points are symmetric, what can we say about delta y? Well, hopefully you guessed it, but essentially those delta y's are the same, because the curve is symmetric. So, if we were to summarize what we've learned from this visualization, a couple of things. The path of travel is symmetric from the start to the finish. It's symmetric about the line of delta y max, meaning from the ground to the peak of the curve. At the peak of the curve, the y velocity is 0. Also, throughout the entire journey, the x component of velocity is the same throughout at any point. The y component of velocity changes, and across the line of symmetry, the magnitude of the y component of velocity is the same, but the direction is opposite. Also, the only acceleration we experience is the acceleration due to gravity, which is 9.8 meters per second squared downwards. So that is a summary of what I just talked about. Okay. Hopefully that's understandable. It's a lot to digest, but with some practice, we'll be able to understand it. So here's a couple of super helpful equations. Again, I always suggest to memorize equations, but these can be derived. I won't spend time deriving these equations now. For now, we can just look at them, discuss what they mean, but maybe in the future I can do a derivation of these equations. So first we introduce this variable called r, capital R, which stands for range, which is the maximum horizontal distance of a projectile launched at an angle of theta with initial speed v naught. So obviously, if we go back to this soccer ball example, well, we didn't really define theta and v naught, but now we've just discussed them. So what is theta and what is v naught? Well, if we consider this horizontal here, the initial velocity that this ball experiences, perhaps from a kick, is, I'm going to change the thickness of this. It's a vector that looks like this, right? Because that's the path that the ball continues to travel. That's the initial velocity. So we can label this to be v naught. And theta is the angle that v naught makes with the horizontal. So theta is the angle between v naught and horizontal. So what does that look like in this diagram? Let me change colors. What color are we use? Let's do pink. That would be this right here. That is theta. And you guessed it, on this side, this is also theta. But usually we just are curious about theta when the ball is being kicked off or when something is being launched. So now that we have those defined, obviously we can change v naught and theta with different, projectile motions. For example, when I kick this ball, I don't always have to provide the same velocity and at the same angle. If I wanted to, I could kick it at, I could kick it at this velocity, not as high up in the air, and that would give me a different theta value. So these values can change. V naught would just mean that I kick it harder or softer, and theta is just the angle. I'll just put strength, but in quotations because it's not really strength. So this formula will give us the range, which is how far the thing will travel, the horizontal distance, delta x. And here g equals 9.8 gravitational constant. Similarly, we can find the maximum height of the projectile. So this is delta y max, right? If we go back, it's this quantity right here. So that's given by h. And if we have the initial vertical velocity, so this means we need the y component of velocity. If we have that, we can plug it into here and we'll get the height. So these are just a couple of equations that can really help you out, save you a lot of time, but you can compute these values in other ways. Now, before we get into some problems, a couple of tips to make you succeed, and you'll notice a lot of overlaps between these tips and the tips presented last week. But first is the tip given in bold, which is to clearly label the given values into the x direction or y direction. So I said a couple of times now that it helps to break these problems into the x components and the y components. And separating all of the givens into these two sections will help us out with our calculations. We won't get confused between what values we have. Additionally, I don't think I mentioned this, but this should be very important, is to label directions. So this is similar to what I did with the soccer ball, where I said this is the positive y, this is the negative y. This really helps us out. We need to be careful of signs, especially when it comes to acceleration, whether or not we want a positive or negative 9.8 meters per second squared. So that's an important thing to do as well. And now most of the remaining tips are tips we saw last week. Write down all of your known variables, figure out the variables that are unknown, which one you're trying to solve for, and then you choose the kinematic equation that has all but one of the known variables, and the last variable in that equation should be what you're trying to solve for. From there, you can just plug your values in, solve for that missing value, then make sure that the direction matches if it's applicable, and then finally check to see if your answer makes sense. And you can use your intuition for this if it makes sense, but usually it doesn't because we deal with some random quantities. So those are some tips. So we can start to see a lot of overlap between both the content and the tips from this week and last week. So with that said, we're going to start with question 1, which is titled Goal with a question mark. But before we get into that, I'm going to get a little sip of water. but we can read the question right now. I'll give you some time, and then we'll jump into it. Okay. Whoops. So the question reads, Cristiano Ronaldo wants to show off his skills. At midfield, he's about 50 meters away from the goal. He strikes the ball such that its initial velocity is 20 meters per second at an angle of 30 degrees from the ground. And we'll start with part A, which asks for how long is the ball in the air. Okay, so I'm going to draw a little picture. And I am no artist, so you're going to have to bear with me. So essentially we have this like ground here, and we have Mr. Ronaldo standing right there, and we have like this goalpost is, somewhere here. And then we have a soccer ball, which is like this, and he kicks it, and it flies through the air, and we don't really know where it lands, but let's just say it lands there. So, what do we know? We know that he's about 50 meters away from the goal. So what is that? That is delta x, right? It's a measure of displacement. Meters is the unit for displacement. And it's not measuring it in the y direction. We're not, comparing the ground level to some point in the sky. We're comparing points on the ground level. So we have that this distance right here is 50 meters. What else do we know? The initial velocity is 20 meters per second. Actually, what I'm going to do is we're going to add a page, just so we have some more room, and I'm just going to, whoops, that's not what I wanted to do. Okay, we're going to try this again. Add a page. Not there. Oh no! Okay. And then we're gonna just change this. And we'll make it a little bit bigger. Now we can see things a little bit better. So we're given that the initial velocity is 20 meters per second. So what is that? Well, its initial velocity, I just told you that. So this is v naught. So what does that look like in the diagram? Well, it's the initial velocity, and we haven't been told whether or not it's in the x or the y direction. Because it's really not in either. It's at some direction in this space, like this, but we are provided that it's 30 degrees from the ground. So that is theta, right? That is theta, 30 degrees. So, if we draw this like horizontal here, and then, we include theta. So theta equals 30 degrees. Okay, and that's all the given information that we have. So question A is asking for how long is the ball in the air? So what does that mean we're solving for? That means we want time. T equals question mark. So this seems a little bit challenging. How are we going to get started? Well, the first step is usually to, break it into the x and y components. Take the quantities we're given and break it into those components. And really, we're only given velocity that's at an angle. Everything else has, some direction associated with it. That's x or y. Namely, the displacement is delta x in the x direction. So what we can do is we're going to take the velocity vector, and I'm just going to sort of redraw it here. Let me use red, so that way it's the same. And we know that from the ground, this is 30 degrees. So what we can do is, now I'll change to purple, is again, we can drop down the perpendiculars. And what do we get? This we can call the x component, the x, and this, we'll call the y component Vy. And now it's just a little bit of trigonometry to get these components. It should be clear that if we label this V, V naught rather, it should be clear that V naught equals V naught squared equals Vx squared plus Vy squared, right? That just comes from the Pythagorean theorem. This is just the vector sum. So V naught is the vector sum of Vx and Vy. So what can we do from here? Cosine of 30 degrees, what's that equal to? That's equal to the adjacent, which is this side. So that would be Vx divided by the hypotenuse, which is this side. So divided by V naught, and that tells us that Vx equals V naught times cosine of 30 degrees. Similarly, sine of 30 degrees, that's opposite, which is this, Vy, divided by hypotenuse, which is V naught. So that's Vy divided by V naught, which tells us that Vy equals V naught times sine of 30 degrees. Cool. So we have these components now. And let me just rewrite it here. Vx equals V naught times cosine of 30. And, well, we can actually solve for Vx because we're given V naught, right? V naught is given here, and this is equal to 20 meters per second, right? If we scroll back 20 meters per second. So this is equal to 20 times cosine of 30 degrees, and if you use your calculator, you should see that this is equal to 10 root 3 meters per second, which is like 17.3 if you have it in decimal form. Similarly, Vy equals V naught times sine of 30 degrees, and this is 20 times sine of 30 degrees, and this is simply equal to 10 meters per second. Alright, so it seems like we're getting somewhere. But now we really want to focus on the time. And for this, let's focus only on the y direction. Rather, before we even do that, what is something we know about time? Well, what I'll say is that the time in the x direction should equal the time in the y direction. So that seems a little confusing and also a little bit obvious. And so, like I said, we analyze this problem in both components, either the x direction, the y direction, or both. So, what happens to this ball in the y direction? If the ball doesn't move in the x direction, but it follows this path in the y direction, it just goes up until it stops, and then it comes back down, right? That is the y journey. That's the journey in the y direction. And what's the journey in the x direction? I'll just label this y direction. In the x direction, well, now we don't care about how it moves in the y direction. It just goes until the ball hits the ground eventually and reaches some other point. So the time it takes to go from here to here, we'll call that tx, and the time it takes to go up and back down, which we'll call ty, that should be the same, right? There's no way that this ball can reach here going this way before it lands back down. Like, that doesn't make any sense, right? Obviously, they should be the same, right? So tx equals ty. So, with that out of the way, let's just consider the y direction. So, what do we know about the y direction? Well, not much. But we can know stuff. And to do this, we need to make sure we label our directions. So, let's say this is the positive y direction going upwards, and going downwards is the negative y direction. And let's just say that the ball starts out at y equals 0. We're just putting a reference point. And we talked a lot about reference points in the last lesson. So we're just saying that the ball starts at this y equals 0, and then it moves to different points, y equals 10, y equals 20. It doesn't really matter. It just starts at y equals 0. So, in the y direction, the initial position in y is y naught, that's just a variable I'll use, and that's equal to 0, because that's what we defined up here. But the ball eventually reaches its final place, which is also on the ground. So that means at the end of the journey, after it flies through the air, it's still at y equals 0. So final position in y equals yf equals 0. So what does this tell us? This tells us that delta y equals the final minus the initial. That equals 0 minus 0 equals 0 meters. And I won't actually box that because that's not our answer. But this should kind of make sense, right? When we kick it, when we're comparing the starting and ending positions, the ball is on the ground at both positions. So its change in y is nothing throughout the entire journey. So it might confuse you at first to see that there's 0 displacement even though the ball has moved, but the only displacement is in the x direction. So that's why delta y is 0. So we have one quantity now. What else do we know? Well, we're dealing with projectile motion. So there's some sort of acceleration, and that acceleration is occurring in the y direction, and as we know, this is gravity, right? So this is 9.8 meters per second squared. But because of how we define the directions, and saying that downwards is negative y, we need to make acceleration negative 9.8 meters per second squared. And finally, we know that the initial velocity in the y direction, which I denote VOY. When I first learned physics, I used to call it VOY, so I may refer to it as VOY every now and then, but it's V initial in the y direction. And I thought it was funny because if you know Spanish, VOY is like, it means I go, or at least I think it means I go. It's been a while since I spoke Spanish, but anyways, we computed this already. Why? Because we have this V initial, and we broke it into its components. So really, this Vy here, that's disguised as VOY, the initial y. And similarly, this x here is V initial x, but we're not concerned about the x direction right now. So we have that this is equal to 10 meters per second. So now we have three variables, and we're looking for time. T equals question mark. So we can consult our handy-dandy kinematics equations, and as I, alluded to earlier, I am now an expert on remembering the kinematic equations. So the equation we will use is delta y equals v naught, and I'll put y t plus 1/2 a t squared. So this equation is this one. Except we just replace the x's with y's, because we're just dealing with a different direction. It's still one-dimensional, because we're dealing with y only, but since we're dealing with y, I don't want to have x's in my equation. So I just put y's instead, and you can do that. So this is the equation we'll work with. And, we can isolate for t, but that seems kind of hard to do since it's a quadratic equation with t. So let's just plug in what we have and see what happens. So we have that delta y is 0, that equals v initial y is 10 t plus 1/2 negative 9.8 t squared, right? So if we simplify this, we get 0 equals 10t minus 4.9t squared. And I'm just going to swap the sides a little bit and factor out a t. So we'll get t times 10 minus 4.9t equals 0. So what are the solutions for t? This occurs when t equals 0 or when 10 minus 4.9t equals 0. And this means that 4.9t equals 10 or that t equals 2.04. So we have two solutions, but we really need one solution, right? We can't have two solutions for time. So what do these times mean? What does t equals 0 mean? Why is that there? That's saying that between the start and end of the journey, no time has elapsed. But that wouldn't make sense because at t equals 0, the ball is at its starting point. And if it's saying that the ball is at its final point at t equals 0, then something's wrong. But really, nothing is wrong. And the reason why we have that is because we let delta y equal 0. And it is true that comparing the start position to the start position, comparing t equals 0 to t equals 0, the ball has not moved, so delta y is 0. And that's just what happens when we deal with this symmetric curve, right? We're going to get two solutions for every point, for every delta y, right? Because the distance from here to here, this delta y, that is equal to this delta y over here. So the time for this path and the time for this path will be different, but we'll get the same delta y. So that's why we have this t equals 0. So this is in fact not the solution. T equals 2.04 is the solution, because that accounts for the entire journey of the trip. Alright, so that was a pretty hefty part A, but the other part should hopefully be a little bit easier. Let's look at part B. So I'll just put this here, 2.04 seconds. B is asking, will the ball reach the goal? So we know that the goal is 50 meters away, so it seems like we want to find what delta x is and then compare it to 50 meters. So B, delta x equals question mark. So now we're dealing with the x direction. So now the values are a little bit different, right? But there's some good things about it. First of all, there's no acceleration. This is just a property of projectile motion, which means that velocity is constant. And, well, I claim that we already know what the velocity is. And that's just this velocity up here. This 10 root 3 meters per second. Because we derived this from the initial velocity that was given to us. We just took the x component of it. So at all points in this journey, at every single point, the x component of the velocity is 10 root 3. I want to make sure that's drilled into your brain, because it doesn't matter where we are. We can be at the starting point, right when the ball is kicked. We can be up here, we can be at the peak, we can be somewhere down here. Even right before it hits the ground, the x component will always be this 10.3, or 10 root 3. It's constant, because there's no velocity. There's no acceleration. Velocity is constant, so Vx equals 10 root 3 meters per second. So what do we know about delta x? Well, we know that velocity in the x direction is equal to delta x divided by time. So delta x equals the velocity in the x direction times the time for the journey. Well, we just solved for time right there. And even though that was time in the y direction, it's still the time in the x direction, right? That was explained earlier. Whoops. That was not correct. So we have time as well. We have t equals 2.04 seconds. There's no other time that could possibly make sense, right? We're just looking at this journey. And we already solved for time. So now we just have to plug it in. Delta x equals Vx is 10 root 3 times 2.04. And if you multiply this out, this should give you something along the lines of 35.33 meters. But the goal was 50 meters away. So 35.33 is less than 50, so it will not reach the goal. Not reach goal. So this is no. Alright, so that's part B. Now we'll do part C. What is the highest elevation the ball will reach? Okay, so this is talking about some sort of displacement, and in particular the displacement in the y direction, right? This is the peak of the curve, the highest elevation. So, what do we know about the peak here? We know that at the peak, the y velocity is 0. It's temporarily 0 because at the peak it temporarily stops before it starts to come back down. So, we can just let this be our final velocity, right? And in fact, this will be our final point, and then the start will be our initial point. And then we can just look at that segment of the journey and see what happens, right? So, part C. Let Vf be the velocity at the final point, which we will just say is at the peak. Then we have Vf in the y direction equals 0 meters per second. We have Vf in the x direction is equal to 10 root 3 meters per second. Why? Because the velocity in the x direction is the same at all times. That's just something that holds true. What else do we have? Acceleration is equal to negative 9.8 meters per second squared. Again, it's just gravity. And we need delta y, which is question mark. Okay. And lastly, we do have from before the initial velocity in the y direction was 10 meters per second. So we have final, we have initial, we have acceleration, we need delta y. 3 variables are known, 1 is unknown. We can use kinematic equations. So this time we'll use Vf squared equals V naught squared plus 2a delta y. And again, we've seen this equation before, except it was delta x. I just changed the variable to y because we're dealing with the y direction. And we're going to first isolate for delta y, so 2a delta y equals Vf squared minus V naught squared. And that just tells us that delta y equals Vf squared minus V naught squared. All of this over 2a. And if we use this, I'm just going to copy it and put it down here. This tells us that delta y is equal to, well, with substitution, 0 squared, right, because that's the final velocity, minus 10 squared, initial velocity. All of this over 2 times negative 9.8. This gives us negative 100 over negative 19.6. And the negatives cancel, and we see that this is equal to 5.10 meters. So what does that mean in context here? That's saying that this height right there is 5.1 meters. And if you're not familiar with the metric system, like measurements in real life, 5.1 meters, that's like 16 feet or something. So that's actually pretty high. Cool. D. This is a nice, easy question. At what angle should Ronaldo kick the ball to make it go as far as possible? And, we can prove this by different ways, by analyzing the angle, looking at the sine and cosine. But this question does appear often, sometimes as multiple choice. By the way, I should probably write this answer. 5.10 meters. So this question does appear quite often, and this you should just know immediately. You should have it memorized. And the answer to this is 45 degrees. And the reason is because at theta equals 45 degrees, both sine and, sorry, that's not a good wording. Sine and cosine are maximized in relation to each other. So that seems a little bit confusing. Sorry, I hit the mic. But really, at theta equals 45, sine of theta equals cosine of theta equals square root of 2 over 2. And as we start to change theta, one of those quantities, either sine or cosine, gets larger, whereas the other one starts to diminish. So at 45, we're at the sweet spot where they're equal to each other, and that's just the angle that you want to kick it to make it go as far as possible. So whenever we see a question asking like, what angle should something occur at to make it go as far as possible, it's usually 45 degrees. And now the question is asking, how far will the ball go if Ronaldo kicks it at that angle? So now we're essentially doing parts A and B again. Really just part B, but we need part A to solve part B. And we're doing it again with theta equals 45. So let me add another page because we ran out of space. And actually what I'll do is I will copy this drawing once again. The artwork is impeccable. But let's just see. So now we have theta equals 45 degrees. And we'll just assume that the initial velocity is still 20 meters per second, and I guess this height won't be 5.1 meters anymore, but everything else is the same. The labels for positive and negative y direction, the y equals 0, everything else is the same. So the first thing we did was computed the x and y components of velocity. So I'll do a quick sketch here. This is v naught, right? And then we can draw the perpendiculars. This is v naught x, this is v naught y, and then we have somewhere in here, this is theta equals 45 degrees, and then what does that tell us? Sine of theta equals v naught y over v naught, and then if we just simplify this a little bit, we get v naught y equals v naught times sine of theta. And if you do a similar thing, v naught x equals v naught times cosine of theta. Cool. The next thing we did is, well, we want to find delta x, right? So let's just write that out first. We know that vx, that's not good handwriting. We know that vx equals delta x over t. And that tells us that delta x equals vx times t. So we have this vx already, but we need the t. And last time we did, we just stole t from part A, so now we have to do the computations again. So to solve for t, look in y direction. This is basically what we did before. And now I'll do it a little bit more quickly since we've already seen this once. But in the y direction, we have delta y equals 0. We're comparing the starting point with the ending point. What else do we have? We have v initial y equals v naught times sine theta. And now I'll plug in some values. 20 times sine of 45 degrees, which is equal to 20 times root 2 over 2, which is equal to 10 root 2 meters per second. What else do we have? Acceleration equal to negative 9.8 meters per second squared. and time is what we're solving for. So we'll use the kinematic equation we used last time, delta y equals v naught yt plus 1/2 at squared. And now we can start solving for t. 0 equals 10 root 2 t plus 1/2 negative 9.8 t squared. And I won't compute this all out. I'll just give you the answer. So t equals 0 or 2.886 seconds. We know that this answer is wrong, as discussed previously. So this is equal to t. And now we can finally bring this back around here. Delta x equals vx times t. And vx, this is from up here. This is equal to 20 times cosine of 45 degrees. And that's equal to 20 times root 2 over 2, which is 10 root 2. So this is equal to 10 root 2 times 2.886. And when we finally compute this out, we should get 40.81 meters. So even if Ronaldo kicks it at 45 degrees, which would maximize his distance, it still won't reach the goal. Now, obviously, in practicality, if we were to try this out in the real world, first of all, he'll make it because he's Ronaldo. Second of all, it will go in because after it lands here, it'll still continue rolling, right? When you kick a ball, it doesn't just land and stop. Right, it rolls. But we're not concerned about that right now. We're just considering what happens at the end of its projectile motion. So, yeah, even in this case, it won't reach the goal. So, in order to reach the goal, he would have to increase his initial velocity, right? Provide the ball a better initial velocity than 20 meters per second. So that is question 1, and that was a very lengthy problem, but it went over a lot of important things that we'll see in two-dimensional kinematics, so I think that was a really helpful one to start out with. Question 2 should be a little bit shorter, and this one is called This Grill is on Fire, and I thought that name that I came up with was pretty creative. But again, this is another quintessential two-dimensional kinematics question, so we can read it briefly. I'm going to get some water again. Okay, so we're dealing with something similar, right? Except now instead of a soccer ball, we're dealing with water from a hose. And excuse the dotted line, but really it's following a parabolic path. Except it's getting cut off at some point, right? This path would continue until we reach the same height. But it's being cut off when it reaches the fire. Right? So, let's just read the problem. Someone had the silly idea to grill some hamburgers inside of their apartment. Unfortunately, the room caught on fire, which is quite unfortunate. Firefighters need to know at what angle they should aim their water hose as to reach the room on fire. The building is 100 meters away from the firefighters, and the fiery room is 60 meters above the ground. Water escapes the hose at a speed of 120 meters per second. So, first, before we get into what variables we have, let's define direction. So we'll say this is positive y. We'll say negative y is downwards. We'll say that negative x is to the left, and positive x is to the right. And we'll just say that it starts out at some y equals 0. So what are we given? The the building is 100 meters away. So this delta x distance is 100 meters, right? It's delta x because it's displacement in the x direction. Additionally, the fire room is 60 meters above the ground. So we'll just assume that the firefighter is, shooting it from the ground. We won't worry about, it's being held up in the air. That's just extra stuff. So that's just saying from this y equals 0 to this fire, this is 60 meters. And that's some delta y quantity. And finally, we're given that the water escapes the hose at a speed of 120 meters per second. So we have this velocity vector which follows the dotted line, or rather the dotted line follows the vector. And this is some v naught equal to 120 meters per second. And they want to know at what angle, so theta equals question mark, right? Let's just put it here. This theta, what is that? So it's a similar question, right? Something flying through the air. Now we're just solving for a different variable. So it should follow a similar strategy. So, what's the strategy? First, let me just write down neatly what values we do have. So we have delta x equals 100 meters. We have that delta y equals 60 meters. And we have that the initial velocity is 120 meters per second, right? And we want to solve for theta. So how can we use theta in our computations? Well, using this velocity vector, v naught, we can do the thing we always do, where we break it into its components, right? So this is v naught x, this is v naught y, and this is theta right there. And if we do a very similar thing, sine of theta, this is equal to v naught y over v naught. So that just tells us v naught y equals v naught times sine of theta. So we see a theta in this equation. Similarly, if we take the cosine of theta, we get, with x's now, that v naught x equals v naught times cosine of theta. Cool. So now we can consider one direction at a time. One direction. But anyways, let's start with the x direction, right? The x direction is pretty simple since there's no acceleration. So x direction. Well, how are we going to solve for theta? We need to somehow relate the x direction and y direction together, somehow, and then we can solve for theta. And how do we normally relate the x and y directions? And I talked about this a little bit a couple of minutes ago. We do this by time, right? Because the time in the x direction is the same as the time in the y direction. The other variables in each direction, they can differ, but time is always the same. So we know that Vx equals delta x over time, and this tells us that time is equal to delta x over the velocity in the x direction. And, well, we have delta x, right? That's given up here. So that's 100. And Vx, well, that's right here, and that's constant. V naught times cosine of theta. So we don't really have the time as a number though, right? We have V naught, and in fact, let's simplify this a bit. This is 100 divided by 120 times cosine of theta, and that equals time. So if we can get this as an actual number, then we can solve for theta. So to do this, we look in the y direction. So, what do we have in the y direction? Again, we have v naught y, that is equal to, that's equal to v naught times sine of theta, which is just 120 sine of theta. We have an acceleration, right? Gravity. This is negative 9.8 meters per second squared. And that's due to how we define the direction of the y direction. And also we have delta y. That's equal to 60 meters, right? That is this height here from where the fire is, or where the water is coming from, to where the fire is. The change in height. And we want time. Time equals question mark. Well, we have 3 variables that we know. We have 1 that we don't know. Let's use kinematics. And we'll use this equation again. Oops, that's not right. V naught yt plus 1/2 at squared. And we're solving for t. So let's just substitute. 60 equals 120 sine theta times t plus 1/2 times negative 9.8 t squared. So at this point, it's kind of annoying to solve for t and then substitute that in here. So instead, we'll just substitute this equation into here. So we get 60 equals 120 sine theta times 100 divided by 120 cosine of theta. And then this is minus 4.9 times 100 over 120 cosine of theta squared. So now we have just one variable, theta, and one equation. So we can just solve for theta like anything else. And I won't go through the algebra because that would take quite a bit of time. So we can just use the calculator and we should get that theta equals 33 degrees or 87.9 degrees. So there are 2 solutions, and this is fine in this case, that we can have 2 solutions for theta. This just comes down to a couple of things. It comes down to the curve being symmetric. So essentially what it's saying here is that if theta is 33 degrees, then the water will reach the fire on its way up, meaning that the peak hasn't occurred yet, right? It might get to some peak further along and then come back down. When theta equals whatever the other number was, 87.9, then it's going like up, and then the peak occurs up here, and then on its way down, it reaches the fire, right? So that's how we can have 2 solutions. I kind of wrote over the question, but hopefully it's still understandable what's going on. So either of these solutions are acceptable. Cool. And that's question 2. So let's move on to question 3. And now we have some multiple choice, so this one won't be as involved as the previous questions. So, what do we have? We have a ball is thrown and it follows a parabolic path shown above. Air friction is negligible. Point Q is the highest point on the path. Points P and R are the same height above the ground. How do the speeds of the balls at the 3 points compare? This is a fantastic question. So, what is something that we know, and we should know this by now because I've said it so many times? We know that velocity in x direction is constant, right? There's some velocity here, which is the same here, which is the same here. I guess those aren't equal-sized arrows, but you get what I mean, right? It's constant. What can we say about the y component of velocity? At point P, the ball is on its way up, so it still has some sort of y velocity. At point R, the ball is on its way down, so it has y velocity in the negative direction. At point Q, we're at the peak. So, what did we say about this? Y velocity equals 0. So already from this, we should know that velocity at Q is smallest. Right? Because there's no y component. The other two have y components, and the x component is the same as at Q. So, from this we can eliminate A, we can eliminate B. We are also given P and R are the same height above the ground. And remember, this is a symmetric curve, right? So what did we say about points that were at the same height? We said at the same height, the magnitude of velocity is the same. but the direction is opposite. But right now we don't care about the direction, we just care about the magnitude. How much is the velocity in the y direction? Because we're going to be computing the net vector anyways, right? We're computing that regardless. We just need to know the size of the y component. And it's the same. So that means VP equals VR, which means D is our answer. And then we have the second part, which is asking which best shows the direction of acceleration of the ball at point P. This one should be pretty obvious. What is the only acceleration when we're dealing with projectile motion? Gravity. And which way does gravity point? Downwards. D. Alright, question 4. It's another multiple choice, but this one requires a bit of computation. So, a target T lies flat on the ground 3 meters from the side of a building that is 10 meters tall. Above, a student rolls a ball off the horizontal roof of the building in the direction of the target. Air resistance is negligible. The horizontal speed with which the ball must leave the roof, if it is to strike the target, is most nearly one of those options. So, we have a nice little diagram, right? So this is like, this 10 meters is delta y, right? That's the change in the height of the ball. This 3 meters is delta x, right? Because we're looking at when the ball just leaves the roof. What can we say about the velocity when the ball just leaves the roof? It only has an x component. It doesn't have a y component to it yet because the student is providing it a velocity to start out with, and it's rolling flat. So it doesn't have any sort of movement in the y direction. Until we have this gravity, right? Gravity provides a change in velocity in the y direction. And again, we'll define positive y, we'll define negative y to be like this. This will be positive x, this will be negative x, right? So this means acceleration is negative 9.8 meters per second squared. Cool. And now it's asking, what is the horizontal speed? So that is this. This is this velocity, the velocity in the x direction, which we know stays constant throughout the flight, right? It eventually comes down like this. And that stays the same. So, what can we do? Well, we know that Vx equals delta x over t. We have delta x. We have delta x equals 3. I'll just write that out, 3 divided by t. To get t, once again, we have to look in the y direction. So let's change colors, y direction. What do we have in the y direction? We have the initial velocity is 0 meters per second. That's right here. So initial is 0, as I just explained. We have the acceleration, right? A equals negative 9.8 meters per second squared. And we have delta y equals 10 meters. And time equals what? So once again, we turn to our favorite kinematic equation. It seems like it's being used all the time. And you guessed it, it's this one. And we're just solving for time. So we can just substitute. This is equal to 10 equals 0 times t plus 1/2. This becomes 9.8 t squared, right? So 10 is equal to 4.9 t squared. And then t equals 1.428 seconds. And then from that, well, we can just substitute Vx equals delta x over t. That equals 3 divided by 1.428. And if we solve for that, we should get 2.1 meters per second. And if you compare it to all of these values, it's less than 3. Square root of 2 is like 1.4. 3/10 is much less. It's very close to this value of c. So that's our answer. question 5, we're nearing the end. I'm going to get hydrated once again. That's my bad. Okay, so now we're looking at these cannons, and they're firing these shells in different ways, and we want to know which shell will have the greatest range. So if we remember, one of the helpful equations I provided was range equals v naught squared times sine of 2 theta divided by g. So g is a constant. So really what we want to do is maximize, we want to maximize v naught and sine of 2 theta. Okay. So, which one will we say is the more important term between v naught and sine of 2 theta? In my opinion, it's v naught. And I'll tell you why. Sine is a function that alternates between -1 and 1. So when we're multiplying by that number, it's only scaling the overall product just by a little bit. Whereas v naught can take on essentially any value, and we're squaring it. Right? We're squaring it. So if we have a really big v naught, then it would be really good for the range. And that just makes sense, right? If you throw a ball really hard, with a really hard speed, really fast speed, very large v naught initial velocity, that ball is going to travel a lot further than if you just toss a ball lightly, even if it's at the best angle, which is 45 degrees. So it makes sense that we prioritize v naught over theta. So already, we can probably start to eliminate some of these answers. You know, D seems like the best, right? It has this huge 100 meters per second. A just seems incorrect, right? The theta, 2 theta will be 60 degrees, sine of 60 degrees is square root of 3 over 2. Well, that's like 0.8, and then we square this value, right? And note that we're also given the mass, but mass doesn't matter, because that's the equation for range. And then B and C are quite similar. The only difference, is the mass, and that doesn't matter. So B and C are pretty much identical. And right now we should be feeling pretty good about choice D. And we can confirm our suspicions because we know mass doesn't matter, which means B and C are essentially the same thing. And we can't choose one of them. So these answers must be incorrect. And then between A and D, it should be pretty obvious that D is the best option. And we can check this by plugging these values into the equation for range, but that takes a little bit of time. This is more of an intuitive approach. So now we move on to question 6, which is the final question of today's lesson. It has a couple of parts to it, but we'll get through it. It'll be fun. These won't take too much time. So a ball of mass 0.5 kilograms, so we're given a mass, but we haven't really dealt with mass whatsoever, so maybe we can ignore it. Initially at rest, so that tells us that v naught equals 0, maybe. It's kicked directly towards the fence from a point 32 meters away as shown above. I'm actually going to erase this. It doesn't matter too much, because now we know that it's kicked, right? So the initial velocity we care about is the initial velocity after the kick, right? The ball can just be sitting there for who knows how long. It's just when, Ronaldo comes up and kicks the ball, or Messi comes up and kicks the ball, that we actually care what is the initial velocity of it. But we're given that it's, oh my goodness, technology today is unbelievable. 32 meters away. So that is this. Delta x. Should be quite familiar. The velocity of the ball as it leaves the kicker's foot is 20 meters per second. Hey, now that seems like a v naught. At an angle of 37 degrees, so that's our theta above the horizontal. the top of the fence is 2.5 meters high. The ball hits nothing while in flight, and air resistance is negligible. So we want the time it takes for the ball to reach the plane of the fence. So that just means it has to reach this point, 32 meters away. Okay, we can do this. So first, let's solve for the components of velocity, right? So I'm going to do that up here. We're given this v naught, and then we break it up. This is v naught x, this is v naught y. It's pretty bad drawing. This is theta equals 37 degrees. We can do the computations again, but we'll see that v naught y equals v naught times sine of 37 degrees, and v naught x equals v naught times cosine of 37 degrees. So you can do the trigonometry there, double check it just to make sure. And we can actually compute these to be 20 sine of 37 degrees, and this is 20 cosine of 37 degrees. Okay, so what can we do? We want the time it takes for the ball to reach the plane of the fence, which is 32 meters away. Well, what do we know? We know that Vx equals delta x over t, which tells us that t equals delta x over Vx. We have delta x, and we have Vx, so we can just substitute and solve. This is equal to 32 divided by 20 times cosine of 37 degrees, and if we compute this out, this is just like 32 divided by 15.97, that is equal to approximately 2 seconds. So that's part A, already done. Now it's asking, will the ball hit the fence? If so, how far below the top of the fence will it hit? If not, how far above the top of the fence will it pass? So that's saying that the ball either does something like this, where it hits here, and then we want this distance, or it does something like that, and we want this height, right? Something like that. It's a bad drawing, but it is what it is. So what are we solving for? We're solving for delta y at x equals 32 meters. We'll just say that this is x equals 0 and y equals 0. Okay. Alright. And we know that it takes 2 seconds to get there. 2 seconds to get to fence. We just solved for that. Okay. So let's look in the y direction, right? So we know that v naught y, the initial y velocity, that's equal to v naught times sine of 37 degrees. So that's 20 times sine of 37 degrees, and we're given this here, so that's equal to 12 meters per second. We know acceleration is negative 9.8 meters per second squared, and time I already said is 2 seconds. So, you probably guessed it, kinematics, equations. And you probably guessed it, our favorite one, delta y equals v naught yt plus 1/2 at squared. And what are we solving for? We're solving for delta y, so it's already isolated, so that helps us out a lot. So this is equal to 12 times 2 plus 1/2 negative 9.8. 2 squared. This is equal to 24 minus, I believe it's 19.6. Yeah, I think that's correct. And this gives us approximately 4.4 meters. So that is saying this height is 4.4 meters. Because this is from y equals 0, right? Because we started at y equals 0. So to find how far above the top of the fence it'll pass, we have to subtract this 2.5 meters from it. So 4.4 meters minus 2.5 meters equals 1.9 meters above fence. Cool. So that's part B. Part C, I. On the axes below, sketch the horizontal and vertical components of the velocity of the ball as functions of time until the ball reaches the plane of the fence. So now we're just doing the horizontal component with time. So this should be pretty easy, because the horizontal component of the velocity is constant, right? When we have this path here, it's the same everywhere. I've done this many times, so hopefully we get it by now. And what is this component of velocity equal to? Well, that's just equal to Vx. And that we solve for up here, 20 cosine of 37, which is 15.97. So 20 times cosine of 37 degrees, which is equal to 15.97. So literally, that's all we need to graph. I'll do it in red. That's it. That's our graph. Because as time changes, the velocity stays the same. However, we can't just say that that's it, even though I just said that's it. We need to be careful of when the ball reaches the ground, right? Or when the ball reaches the fence in this case, the plane of the fence. So at some time t, which in this case is t equals 2, at t equals 2, the ball is at the fence. So we don't want to draw the entire graph, we're only going to draw until t equals 2. Right? Because at that point, the ball reaches the plane of the fence, and it's not asking us to sketch beyond that. So that's that. And finally, the last question of the day. It's an easy one. It's just the same thing. Now we're doing the vertical component of velocity. So this is asking for Vy. Well, we know the starting Vy, right? That was computed here, 12 meters per second. So we can plot that. And we know that we want to end at t equals 2. What else do we know? We know acceleration in the y direction is negative 9.8 meters per second squared. And then what's the relationship between acceleration and velocity? The slope of velocity versus time graph equals acceleration. So we want the slope of this graph at all points to be negative 9.8, because that is the only acceleration being experienced. So this should be a linear graph, right? A line with slope negative 9.8. And so at t equals 2, we actually end up somewhere down there. Oh no. Oh man. There's some technical difficulties. But since we're reaching the end, I'm not going to bother with resolving those technical difficulties. But essentially what happens is we draw a line with slope negative 9.8 that passes through the point that we marked on the y-axis. So you can imagine it's something like that. And that's it. That's today's lesson. So hopefully that was helpful for you today. We can sort of see how 2D kinematics branches off of 1D kinematics. There's a lot of similarities. We can see that some equations are used a ton, and there's a lot of things that we have to know right away, that the horizontal component of velocity is the same throughout. So yeah, hopefully that was helpful. I think these problems should really give you a good insight into what kinds of problems you'll see on exams in class, as well as on the AP exam. And if there are any further questions, just video will be posted on YouTube. If you're watching on YouTube, please feel free to stop by for our stream so you can ask your questions in real time so I can answer them for you in real time. Just a reminder of our schedule. We stream on Mondays, Wednesdays, and Thursdays. Mondays are AP Physics 1 content. Wednesdays are Calculus content. And Thursdays is AP Physics C content. And then every once in a while we'll throw in some bonus streams for the SAT, AP Lit, AP Lang, stuff like that. But yeah, that's going to conclude today's lesson. I had a lot of fun. This is a really fun topic because now we're dealing with things that move in space. So yeah, hopefully you learned something, and I hope you tune in next time, and hopefully you learn something. So take care. Until next time.